Yes, and as usually I switch to English just to not to mess up with um, terminology, which will be terrible svengelska, kan man säga. So in this week is dedicated to public key cryptography. So I selected two topics for you. So one, and both topics are of very high practical importance. And just to make it relevant to your day-to-day experience, I want to probably switch to my web browser for a second and show you something connected to the topic of this week. So let me see. Yes. Now I need to get rid of this thing. Let me see. Yes. So, for example, so we visit this web page or any web page that has in its address this HTTPS. I guess you know all what this means, but if you're unsure, so this HTTPS stands for a secure HTTP. And it's a web protocol for retrieving web content. And S stands for secure version of it. And the security in this context is provided by a lower layer or a protocol. So if you remember the course taught by Chen Wei, so computer and network communications, so there are different layers in the communication stack. So while web application is a functionality of so-called application layer, so the next to it is a transport layer, which is normally implemented by two protocols, TCP and UDP. And TCP and UDP, they are not secure in any way. But there are needs to implement security. So you want to do several things. Well, for starters, you want to encrypt your communications. For example, when you access web page of a bank, so that all communications could be should be encrypted so that nobody else can attach a computer to a network, so run Wireshark and listen to the traffic. And so we will learn about secure TCP protocol so on the next module, so in 2 weeks from now, when talking about network security. But what is important to know about it at this moment is that this protocol, so it's a protocol of transport layer, so it implements encryption and authentication. So authentication service is about verification that you are you, so that you should be sure that you are communicating to the correct person. And this authentication happens virtually anytime you try to access secure services. Well, as I said, a web page of a bank is one example. Another example would be virtual private network. So whenever you use VPN, so there is authentication going on under the hood. And today we will be talking about the building blocks that allow implementing these services. And so both services, they involved encryption using asymmetric cryptography, algorithms for asymmetric cryptography. And specifically, so what we will be talking about today, today and tomorrow, will help understanding the following. So if you would go into security section of a particular website. So let's try it now. So connection is secure. So if you click on here, so then you see that a record about validity of certificates, so that your web browser verified the validity of the certificate. From the website. So let us have a look what is inside this certificate. So it's a digital document which is issued by some organization. Well, probably here it is. Yes, it is issued by some organization called R10. I mean, we will talk about it again in the networking section module. And then if you look inside, so it has different parameters. So basically somebody tries to verify that this website called dugas.ch is actually a valid website. And this means that this document is created by a so-called certification organization that tells that confirms that such sites exist, and that it has the following. Yeah, at this moment, it just confirms that it exists. And this document is, moreover, electronically signed. So it's electronically signed. So the algorithm that is used for signing is something which is called RSA with PKCS, something. So that we will discover today. And moreover, so it provides a key, so information. So the material that is needed for the web browser, for your web browser, to verify the validity of the certificate. And in this key, you see that there are plenty of numbers, which is called modulus, and then down the lines, you see something which is called public exponent. So altogether, this construct corresponds to a key. So you can use this lots of numbers to apply this to input to the specific algorithm and verify the correctness of the certificate. So I will come back to the exact procedure for generating signature a little bit later. So I can show you another website. So let's now close this one and open our lovely ChatGPT. And we do the same thing here. So we go to security, certificate is valid. So we open it. And again, going into details of this certificate. So if we check certificate signature algorithm, so here we see something different. So we see that it's not RSA, but this is something completely different, ECDSA. So that's what we will cover tomorrow. And then if you look at the public key information, so it is also in very different format. So it just so there is no modulus, there is no exponent. So just a numbers, and these numbers are, altogether, it's just very large integers. So, looking a little bit ahead to the topic of tomorrow's lecture, so this algorithm is based on a so-called elliptic curve cryptography. And this ECDA acronym, so if you look here, so it stands for Elliptic Curve Digital Signature Algorithm. And yes, and the rest of the value here, it means that what is signed with this algorithm is a hash of this document, of the entire document. So a secure hash algorithm, the one that we considered during very, very first week of the course. And by the way, so if you have any questions, so please stop me. So let me see. Yes, that's a good thing. It doesn't. For this very service, for the authentication, I again looking a little bit ahead. So this is the principle of signature, but this is really good to repeat several times. So I will tell about it now. So digital signature is about somebody encrypting a message with its private key that is kept in secret. So in this case, the signature is created by the organization who issued the certificate. So this organization, it has private key, which it obviously doesn't reveal to anyone, and it encrypts the message with this private key. But the beauty of public key cryptography, and that is why it is called asymmetric cryptography. So you may use the other key, which is in this case a public, to decode it. So you see, you encode with the private key, and everybody who knows the public key can decode it. But this is the principle of the signature. Only the one who owns the private key can create an encoded message, and all the rest who knows the public key can decrypt it. So this is the principle of digital signature. So let me go back. These slides will be available right after the lecture. So, and I also focus on these fields, which I just demonstrated to you. So what we will learn essentially during today and tomorrow's class are these details, so that you are able to understand. So what is it? What does it mean, modules? How modulus and exponent coexist? So and how the algorithm works, and the same for tomorrow. So we will learn what is an elliptic curve. So elliptic curve is a mathematical equation of this kind. So and how it can be used to create a ciphertext. So that's what we will learn today. But we will take it so to say, despacito, so slowly. So I mean, there will be some math. So don't be stressed if you kind of don't, follow in super tiny details. My hope is that you will kind of grasp uh, the overall picture, and I will show you what you need to know to, for example, successfully complete Duga. And as I said, so today we will talk about something which is called RSA algorithm and introduce the principle of digital signature. We will see where RSA algorithm is used in practice. And tomorrow we will consider two new asymmetric algorithms. So it's something which is called Diffie-Hellman for secure exchange of a secret over a public channel, and elliptic curve cryptography. Yes, please, Daniel.
Just out of curiosity, because I can also mention that we've covered a bit of this in one of our previous courses, more than we had the other encryption stuff and SQL attacks.
Which
Um,
which one? Which
in
course?
computer networks, we covered a bit about public key encryption, how it works with the private key and so on.
So
But not,
yeah.
yeah.
So just to clarify, I guess you covered a little bit of RSA and the principle of digital signature, and but not at all these two.
Um, I mean, we saw an equation, I think, but that was never like tested properly. The RSA algorithm, I'm a bit more unsure of, but digital signature, we covered the concepts of at
Yeah.
least.
So
Um,
in this case, there will be a little bit of repetitions. That's good.
mm,
But and I will try to explain really the bolts and nuts of the algorithm.
mm,
So how the numbers are generated, so and why. So a little bit of math background to it, and I'm pretty sure you didn't look at this thing. So it's good if there will be some overlap. So that's, but
mm,
I'm pretty sure you will hear something new.
mm. But my question of curiosity was public key encryption, and it's used to verify that only the person holding the private key could create a message that can be decoded with the public key. But what is the plain text? What is the message being encoded? Is it a standardized, like all
Yes.
zeros?
No, 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 no. That's
No.
a good question. A good question. But
Yeah.
maybe we can take it. I mean, so this rather mechanical stuff first. Let me see if I have a slide for that. La, 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 la. Maybe not. Um, Authentication. Maybe it's here. Well, let me be verbal, but I mean, I hope you will get it. So, what you sign. Well, uh, the plain text for starters, it can be any text. So just, I mean, as is the case with symmetric key cryptography, you can turn any text into a number, and then you can try to apply this algorithm that I will tell you more about and do encryption. In practice, you don't do that because of simple reasons. I mean, these algorithms, both RSA and based on the algorithm based on elliptic curve cryptography, is based on heavy math operations. So it's computationally heavy to encrypt. And as such, so you normally, you use it for encrypting shorter portions of plain text information. So what are these shorter portions? For example, RSA algorithm is used to encrypt a secret key for for encrypting the communications. In this case, so you encrypt a key. So you generate a key for say DES or AES encryption, as we learned during the first week, and you use this key, which is 128-bit long number. So you use it as a plain text. And to encrypt, you use the public key of a person to whom you want to send it. So that when he receives encrypted text, so he can apply his private key that is kept in secret, and only he can decrypt the this secret key. And all the rest of communication, so say video or audio stream or text, very large text, will be encrypted using different algorithm, this secret key based algorithm. Are you with me here? So let me see. Is this understandable?
Yeah, we covered this a bit.
Yes, so in this case, it is not zeros. It is really a number, so 128-bit number. And so the second option is what I showed you previously. So it's when you want to create a signature. To create a signature, you again, so you first you cannot you can, or it's computationally expensive to encrypt the certificate in the textual form. So instead, what you do, so you apply a hash function to your text of the certificate. You produce 256 bit number, and then you encrypt it with the RSA algorithm or whatever elliptic curve crypto algorithm. So it is never zero, it is never one, it is always a relatively small number that you encrypt. So either a key or a hash. If I understood your question correctly, maybe I'm answering kind of wrong question.
Maybe I didn't follow, but for checking the certificate, then does the user provide the plain text and
Absolutely.
then check? Okay, so it's not a standardized in that sense. It's the plain text that you send and ask the um,
What you send, as I showed you,
hmm,
this is what is sent. So now it is kind of a graphical form, but it is a standardized format. So this is a certificate field. So it's a digital format, which tells, the values follow one by one. So like first version, then serial number. So this all exists in the plain text. And at some point, up to here, up to some point, it is a clear text. Then you take hash function, which is specified here, and uh, create a hash of this text so that nobody can modify it. And this hash is then you encrypt. So everything is, all steps are standardized. So the electronic format is the digital format is standardized, the hash algorithm is standardized, and the sequence. And that what you will try next week in the lab. So you will take the certificate and try to verify it manually. But okay, so let's move on. So we talk about RSA, and the RSA stands for Rivest Shamir Adelman. It's the first letters of the surnames of the inventors. So the whole algorithm was invented in back in 1978. And its strength is based on a so-called on a hard computational problem, which is called factorization of large numbers. And now you will we will see where these large numbers are come from and what is the factorization. But again, in simple words, given a number which is a product, result of multiplication of two other numbers which you don't know. So it is computationally impossible to find these numbers. So this is a problem of factorization of large numbers. And so the math background which is needed to understand it is a modular operation. So I won't spend too much time on that. So you define kind of the maximum value until which you do all the computations, and then you do computations as normal. So plus multiplications. The only thing is that you then take a reminder of the division on the modular value. Another important thing to understand is the concept, or to remember, is the concept of relatively prime numbers. So relatively prime numbers, so they are, or this relatively prime term is always applicable to two numbers. So you say that one number is relatively prime to another number, and it means that these two numbers have no common divisors. So, for example, if you take 10, so relatively prime to 10 are 1, 3, 7, and 9. So that's kind of clear, right? What is relevant for future presentation of the algorithm? There is another nice property for these relatively prime numbers. So if you do multiplication, some modulo, so only relatively prime numbers, so they have I mean, for them, you can define inverse to multiplication operation. So if you multiply two numbers, say 7 by 3, so it is 21, modulo 10 is 1, right? So 7 by 3 is 1. So it means that there is an inverse operation. So you can you can take this result, divide by 7, and get 3. So so basically 3 and 7, they are so-called multiplicative inverse to each other. And this property will be used, I mean, this is one of the main properties which is used in the algorithm. So let's define the last interesting number, which is called totient function. And this function, which is, well, in our context, will be denoted by phi, it will count all integers which are relatively prime to some given integer. So just the total number of relatively prime to a certain number. And it is obvious that for prime numbers, which which is only divisible by themselves and 1, so this number, so this totient function, is equals to n minus 1. So basically, all numbers up to n are relatively prime to prime number. And then, this rule is valid, so that if you have a product of two numbers, so then the total number of relative prime numbers is the product of corresponding numbers for m and n. And this rule, together with this something which is called Euler's theorem, allows us to do very complex computations relatively simple. So you can simplify certain types of computations dramatically. So, for example, look at this quantity. So you want to raise 4 to a very, very large power. and then take it and do this computation modulo 33. So as you can imagine, rising any number, even a small number, into this huge power, so that's very, very complex for computers. So what we do, we can apply Euler's theorem and simplify these calculations very, very dramatically. So so we start off with the following observation. So number 33 can be represented as a product of 3 and 11. And we can easily compute. So these 3 and 11 are prime numbers. So the number of relatively prime to 3 is 3 minus 1. And a number of relatively prime numbers to 11 is 11 minus 1. So this phi 33 is equals to 20. So, and now what we do for simplification. So we we take this number, which is phi of 33, and try to find a multiplier that together with some additional integer gives you this a large exponent. So it's 5,000 multiplied by 20 plus 3. So, and here, if we trace all the computations, so you see how, how the simplification boils down to very simple computations. So first, what we do, so we take first simplification, and so because of properties of rising to the power, so you can so you represent it as 4 to the power of 20, and the whole result is to the power of 5,000. And then this is a small number, so you leave it alone for a moment. So then again, so this is due to property of modular operations, so so-called distributive rule. So you kind of split this part into two modules operation. So one for this large exponentiation and one for smaller exponentiation. And then you do the same for this exponential over here, so, exponentiation over here. So you can bring this module in the parentheses, so resulting into in this equation. And now, so this is a very interesting stuff. So 4 to the power of 20 modulo 33. So if we look at Euler's theorem, so 33 is n, and 20 is a phi of n over here. So, and this theorem tells that anything with n and phi n over here, so it boils down to 1. So, and you see, so we simplified this quantity over here to computation of 1 to the power of 5,000 and multiplied by 64, which is 4 to the power of 3, and taking model. So this is a very simple computation, which results in 31. So this, I'm telling you just to illustrate the interplay of different mathematical relations between prime and relative prime numbers. So now we start the RSA algorithm by looking at how keys are generated. So what we want to generate, we want to generate a modulus, so using which we will do computations, and we want to generate two numbers, a public exponent and a private exponent. So RSA key is a combination of two numbers. an exponent, and a modulus. And you have two pairs like this. So and one pair you keep in secret, and another pair you publish openly. So correspondingly calling them private key and a public key. So how you do that? And here we come to the really real essence of this computational complexity. So that's what makes the algorithm very, very strong from the security perspective. So you start by choosing two very large numbers, prime numbers, P and Q. When saying large, I mean numbers which are 256 or 512 bit long. So they are very, very large numbers. And you multiply them. And you never reveal which numbers you used for this multiplication. Moreover, so once you computed the product, once you multiply them, you forget this number, so you don't need them anymore. So you just discard them and use only n, so the result of computation for future operations of the algorithm. And it is here that you make it very, very strong. So now, knowing n, you cannot you cannot understand so which numbers were used to produce it. So it can be anything. So and then you choose these two exponents using these two last rules. So you choose exponent public exponent e, which is relatively prime to this function. You remember that this function would be this number minus minus 1. And since this number is relatively prime to this, so you can also find another number that's multiplying these two numbers together, modulo this operation, would give you 1. So that is called finding multiplicative inverse. So this D is the inverse of E. So, it is analogous to division. So, in normal arithmetics. So, and once you found these two numbers, so combination of E and N become your public pair, and D and N becomes your private pair. So let me go back to this slide a bit later. So let us trace the encryption and decryption procedure. So for encryption, and here I really use word encryption to in the privacy service context, so that you want to take a plain text message and produce a ciphertext that nobody can decrypt but the one who owns the private key. And what you do, so you take this message M and you write it to the exponent, to the power of E. And you do this computations modulo N. And just the long story short, the decryption follows exactly the same procedure. So you take the cryptotext and you raise it to the power of D, so this other exponent that you generated. And here is a kind of sketch of a proof. So what is happening? So this M to the power of E D, so is the decryption procedure. So you first encrypted it with the E, and then you decrypt it with D. So now let's see that it boils down to M. So it follows exactly same principle. So when you will study this subject at home, as we did here. So you take the exponent and you do the simplification steps. So this k phi n means that you take some multiples of phi of n and add one. So basically, you take away one of the elements from the product. And the reason for this is that you want to boil down to this equation, which is one, according to the Euler's theorem. So, and in these few steps, you can really see that applying this operation, you can recover M. So maybe not. So now we won't do that. But so at home, so please trace the following examples with numbers, where you start with P and Q, which are prime numbers, and do these steps. So maybe one advice. So when you, so let me see what you have in chat. How does the private key come in? No, that was. To find large prime numbers. Yes. Actually, well, the answer is yes and no. So the question, if you read in the chat, so if finding large prime numbers, difficult task on its own, it is because I mean there is a naive way of testing. So it's all about testing on primeness. So so there is a concept of testing on primeness. So you generate a number, and then you want to find whether it is prime or not. So the very naive way the very naive way is to take this number and see whether it is divisible by all numbers before that. But of course, I mean, the larger number is, so the number of division is prohibitively large. So so there are shortcuts. So there are shortcuts, again, some theorems that probabilistically test the primeness. So there is a way to kind of generate large prime numbers and say that with very high probability they are prime without testing on primeness. So you can probably let me see if I get any decent hint. Yeah, it's a Fermat theorem, so primality test. So so if you go here, so let me just post it in the chat. Yes, yeah, and that is normally how it is done. So you apply this shortcut for this. I have some slides, so I can maybe dig up this information uh, after the break. So soon we will make a break. So maybe now we can take a break, and I will comment on this somewhat more. So let me pause. Oops, what did I do? I stopped sharing. So let me pause the record. Yes. So I dug up the information that I wanted to tell you. So it's somehow. So let me see the original question. I somehow reacted to this comment. So that's the way to get random big numbers is to get random big numbers and to test them for primeliness in an efficient way. Here you touched upon a very interesting problem, Max, because of the following. So if you read the specification of the algorithm. So, and that is how it is presented normally to students. Let me see this one. So probably you were presented to this algorithm in the same way in the previous course. So, and it tells that you start key generation with choosing two large prime numbers, and then eventually you choose E to be relatively prime to this to the multiplication p minus 1 q minus no, sorry, yes, p minus 1 q minus 1. So this is used to compute this phi of n. But in this case, the problem is that I mean, you cannot control the size of E. So this E can be very, very large. And remember why it is a problem. The problem is that the encryption is still rising to the power. So this is very expensive operation and long one. So rising to a very large power for a computer, that's a kind of tricky business. So what and now I want you to go back and practically critically examine this certificate so that I shown you previously. So this is the key value. So this is a modulus. So this is a large number. Blah 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 blah. Blah. So it's 2048 bits integer. So that's a large number. And public exponent. So that's a very interesting thing. So it's this number, 17 bits only. So and if you do conversion decimal to binary, so it's 17. So and that is kind of interesting because so let me go now. So what practically is done for RSA algorithm is that you start key generation with first selecting your exponent, and you want this exponent to be a small number for very quick encoding operation. So, for example, this can be a small prime number like 3 or 17. So rising to the power of 17 is nothing for computers. Rising to a cube is also nothing. Um, so also it generates certain problems. I will come back to it later. But so you start with E, which is small, and then you need to find such P and Q. So you do kind of reverse engineering of the algorithm. So that their product, so minus one from each, is relatively prime to E. And what does it mean? Again, so writing down some simple equations, so it means that p minus 1 and q minus 1 modular exponent. So let me add here that for example 3 or 17. So is actually one. So this is the condition. This is the condition for being relatively prime. So this number relative prime to E, and this number relative prime to E. And this thing. So, for example, E. If you open up this parenthesis over here, so it boils down to this very simple equation. So that P should be equal to modulo 3. But remember, so the important condition for P and Q is that they should be primary. So the practical key generations in operating systems, when you use these APIs and commands to generate keys, so it is done like this. So I mean, one of the exponents is chosen to be small. So then P is computed. So you generate a random big number P. So you multiply it by 3, add 2, and this becomes your candidate. And you run this primeliness test, the one that I showed you, I mean, the link to verify if it is prime. And only then you kind of you generate your modulo n. Are you with me here? Is it understandable? So just to repeat, because of practical reasons, you want to do exponentiation very fast, and for this you need small exponents. And these exponents you select first, and then you kind of reverse engineer these big prime numbers P and Q, which are used to compute your modulus. Yeah, that's totally valid comment, Tony. So I'm not asking you to kind of remember and even understand kind of the details, but again, so here the important point is the concept. So how you uh, I mean, what are the conditions for selecting different numbers, and also the trade-offs from the computation point of view, because you don't want to end up in a rising 256 bits number into exponent which is 1000 bit long. So that's totally impractical. Rather, you want to uh, you want to optimize. So this is optimization step. So now to summarize, what you should probably remember, not remember, but at least to be able to, you need to be able to parse the steps of the algorithm over here. So maybe know this optimization criteria, and also to know that relative prime numbers they are found or computed by a special algorithm which is called Euclid algorithm. We don't go into details of it. So whenever you ask to find, so for example, give an exponent, and knowing this Tottian function which is phi of n. This number. So you could be asked to find D, which is multiplicative inverse to E, so that it satisfies this equation. So for this purpose, practically, so you can use any online calculator. For example, multiplicative inverse calculator. Modular multi. So, for example, this one. So let me see. So integer 3 modulo 26. So let me use numbers from this example. If we have this example with numbers, so we have modulo 221 and E7. So let's find D. So, and for this we so I add here use online calculator. So let me see. So it was 221, and I think it. What was it here? 7. 7. So let's see. Whoa. Did I miss anything? Oh, sorry. 122. So if it should be relatively prime to this number. 192. 192. 192. 55. Okay, so now everything is fine. So you see, let me just copy this, for example, this one. So, and this was to get this number 55. So you need to follow the steps of the algorithm, understand what is used in different parts, and when you're asked to find, for example, D given some number of E, then you can use this calculator. All right. Any questions on this part?
No, I appreciate the example there because it makes it easier to realize what you actually have to do later when maybe you're asked to solve something. So it's just not the numbers anymore. It's like this is what you actually have to do. So that's great.
Yes, absolutely. So yes. And this is more for information. So that's for kind of information on optimization. So how to make algorithm more usable. Because let me drift away a little bit and to the side. I will come back to Oscar, to your question. The main property of any security algorithm is usability. So it should take reasonable time to perform security operations, because if it doesn't take reasonable time, so normally users give up on that. So and this concerns the execution time as well as complexity of the security solution. So I can, as an example of this kind, I can mention a secure electronic mail system, which is called PGP. I don't know. Can you raise a hand if you heard about it? PGP. Is it PGP mail? Yes, pin. PGP mail encryption. Pretty good privacy. So security program that encrypts emails and other blah 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 blah. Yeah, it's a program, so it's yeah, it involves keys, yes. But it's the whole system that somehow allows to create secure emails. And it was created for for confidentiality sensitive electronic exchange. But if you ever tried it once, you would understand how complex it is. So in practice, it is very, very seldom, well, at least, I mean, it is not used on a private basis because, I mean, it's very complicated about, the key generation, the signing procedures and stuff. So usability is the key requirement to good security algorithms. So, and in addition to the strengths of the security. So if it is not usable or badly usable, so humans prefer rather not to use it. And these steps were a comment towards this property of algorithm. So let me see. Is P minus 1 multiply Q minus 1 the inner workings of the algorithm? Yes, it is one of the steps. It is one of the steps here to generate an essential number, which is used to generate E and D. So all these numbers N, E, and D, so they are chosen following very strict mathematical rules. If not chosen by these rules, so the whole scheme wouldn't work. And in this case, so P and Q in this presentation, they are essential numbers where all computations begin with. So I hope it's not confusing. So I mean, on this slide, I just show the kind of reverse engineering of P and Q. So starting with some other number, but this is only for optimization purposes. Yes. Well, let me see. Let me see. So some examples you can follow here. Yes. So coming back to the very first question we had during today's class. So what to use as texts and so in the first place, public key encryption can be used to share symmetric keys for symmetric crypto algorithms like AES or DES, as we discussed previously. And normally it is part of the secure protocols. So before encrypting a message, for example, this transport layer security, so I will show you the diagram later on. But again, on the level of hand waving, it is like this. When you click on any secure HTTP site link, so what happens in the first place, it retrieves the certificate. First, it wants to be sure that I mean your browser wants to be sure that it is talking to the proper server, so to the server of say SEB bank. And to do that, so somebody else, what is called certification authority, the organization that you trust to, so beforehand, like long in advance, conducted a registration procedure for the SEB Bank website and issued a certificate, so textual message saying the details of the website, and then signed this, so created a hash and signed this hash with a private key of the certification of authority and supplied the public key so that anybody who retrieves it can verify that yes, it was encrypted with the private key of the certification site. And then along the line, so when you are sure that you are talking to SEB Bank, you start a phase where you exchange security protocol suite. So the number of security primitives that will be used to encrypt the session. So, and for encryption of actual data, you need to use a secret key algorithm. So because it's fast, it's super fast. And all this, so you will see later on. So during this step, you agree on what kind of encryption mode it will be, like EBC, CBC, C, or whatever. But before doing starting encryption, you need to communicate to the bank the secret key which will be used, and this you do in this way. So you take the key, which will be used to encrypt the content, and you sign it with the public key of the bank. And so only bank now can decrypt the key, and you send it over as part of the connection establishment routine. Any comments or questions on this part? Good. And again, as I mentioned in the beginning, so in principle, you can use any message, converting it to a super large number and trying to raise it to the power. I mean, on the level of definition, so this approach is called textbook RSA. So you take, but in practice, it is very seldomly used. So only when you encrypt the key. So in this case, key is the plain text. It's a short number, and in all other cases, you work on secure hashes. So on message digest. But one should be very careful. So connecting these dots to this thing. So if you encrypt with certain exponent, with a small exponent, so is there any risk for compromising the algorithm? In fact, yes. So if you think about it, so look at the encryption procedure. So this one. So now this E is 3, right? This modulo is large number, so that's produced by multiplication of two large numbers, right? So do you see any risk here with this scheme? So as a hint, I can tell you that this risk is connected to the value of this plain text message that you want to encrypt. Any ideas? So let me wait some seconds. Again, so right, just this line is not tough math. So to say, what you do here, so you take plain text, a number, and you raise it to power, say power 3, so to the cube. And now you need to think along the following line. So this result, m to the power of e, compared to this value, modulo n. No, it's not that it is 0, but it's towards this line, towards this direction, Luca. So one of the strengths of the encryption, except for finding out the way how you generated E and N, so that you can kind of figure out what D is. So in addition to this factorization problem, so we do all the calculations by modulo. So it's always reduction. So you always stay within this. So it's hard to understand the actual number when it is applied modulo. So, but think now if this m is very small, or it is such that when rising to the power of exponent, it is smaller than n. What it means? It means that you didn't encrypt anything at all. So what you can do, you can take this number and you take a cubic root. So that's a easy operation, and you just get back the original m. So what you need to be sure is that this m, when raised to the power, even small power, is very large number, larger than n. And that is why, so there is a requirement on the size of this plain text message. So it should be large numbers, so at least so some hundreds of bits. So this is a possible attack. Another attack of this same kind would be, as it is written here in the last bullet point, you can try encrypt so you can imagine a scenario. So when you ask a system, so for example, you have an encryption block, and you've got an encrypted message, and you know the exponent, but you don't know n, so which was used to produce this encryption. Yes, that's correct, Oscar. So that's m to the power of e have to be larger than n. Yes, that's true. Or practically, I mean Yimi, that what you said, it converts to kind of impractical case when you try to write a large number into some exponent. But that's true. I mean, your answer is also correct. But I mean, the correct, practically correct answer is that m to the power of e should be larger than n. So, so this last item is about, as I said, so you have an encryption machine. So, and you get a hand on encrypted message, and you know exponent, but you don't know n. So what you can do, so you can try do encryption, so of different messages with small numbers. Some number of times using different number of exponents, and then multiply these numbers. So the result will be the same as, well, let me see where it is. The result will be such that when you're multiplying this stuff, so along with the modulus arithmetic, so the number after the modulus will be multiplied. So basically, you will get a huge modulus, and in this case, you may again end up in the situation that you can just take the eth root of the ciphertext, and then it will return you the attack. Then it will return you the message, the plain text message. In order to avoid it, this type of attacks, people introduce padding. So they are smart people. So if you want to encrypt a small number, so you make it big by introducing padding. So to some random numbers. And so that's what this PKCS stuff stands for. So you basically add to your target text, you add some values so that the resulting number is large, and then this m to the power e larger than n holds. And there are a couple of other schemes. So this PKCS number one, so that we have seen in the in the certificate for one of the websites. There is another one. So here you can see the details of how it looks practically using the APIs. And then there is another one, which is, let me see if you see it. So which is another standard for padding, where you generate a random string and then you XOR with your the text, and then you kind of and this random number is standardized basically, so it's known to all. Yes, and that's what we have. What remains to be said exactly as well, I have repeated it already several times. So if you use this algorithm, rising the plain text into the power of public exponent e, then you implement private exponent. Then you implement privacy. You implement signature. So let me say it again clearly without stammering. So let me. That's my daughter calling. Yes. Sorry for that. So if you take a plain text and rise it to the power, which is private exponent, then you implement the signature. Because everybody who knows the public exponent can decode the message. Otherwise, if you rise plain text into the power of public exponent, you implement confidentiality, because only the one who owns the private key can decode it. Is this clear? So the last thing for today, so you can scan all these slides that I talked about verbally. Maybe I can comment on another usage of public key, which is very useful. This scheme is used in credit cards with the chip. So basically, it is based on a public key crypto. So and here is the authentication part of it. So you start by sending the certificate, which is encoded and stored in the card, so to the terminal, and together with the card's private key, and no. So I'm sorry. So private key is preloaded. So it's when the card is created, so the private key is stored on the card. So that's what will be used to provide security services. So what you send over the certificate. And so the terminal knows, and as part of the certificate, you have the issuer. So the terminal knows its public key, and it can decode it and verify, yes, that's the one that I trust to. And from the certificate, it retrieves the public key for this card, and this public key will be used to complete the verification. So the terminal will send you a challenge. So your card will sign it with the private key, and this challenge will be verified using the public key extracted from the certificate. Okay? And the same thing goes when signing a transaction. So you sign a transaction with your the transaction is the input to transaction is coming from the terminal side. So you sign it with the private keys that yes, you agree to withdraw money or to transfer or to pay to somebody, and you send it over. And this is the non-repudiation. So now the terminal can tell that yes, you signed the transaction because it can verify it with your public key. Any questions on this part? Well,
Yeah,
yes,
just a quick question.
yeah.
So which part of this is the PIN number that you usually have then?
Oh, PIN number is just it's a local thing um, I mean it's not connected to private key. So
Okay.
it is kind of first level authorization.
Okay, so yeah, okay. So it's just kind of a gateway into,
Yeah. Yes.
okay,
Into this process. So
right.
first, it's like, do you own the car? So do you know these four numbers? Yes. Then you kind of send over certificate and such.
So it's not actually used. It's not used in any part of the.
Authentication.
No, it's just more of a okay. You belong to that card kind of thing. Yeah.
You know, I'm
So
hesitating.
my
I'm
question is really about if that pin is used as part
key
of
generation.
yeah, exactly.
I kind of, to the best of my knowledge, no.
Okay.
Because I mean, these keys. So the private key can be large. It can be. It is pre-configured. So it's. But again, so maybe I need to dig up this information, or you can do it yourself and tell me tomorrow.
Sure. Yeah, sure. We'll see.
Oh,
We'll see
but
how I get on today. But yeah.
yeah, yeah, yes. But I mean,
No,
yeah. So, sorry.
no, carry on, please.
No, but I mean that's it for today. So I mean we covered quite a lot. So we went through RSA again. And talked about different security services to be implemented with public key cryptography, so signature and encryption for confidentiality. And finally, we considered some possible risks and padding as risk mitigation techniques. So that's it, what I wanted to tell you today. So again, so if you have any comments or requests, shoot. Well, if not, then I see you tomorrow. So thank you for coming today. Hej då, vi ses imorgon.